In this video, we're going to talk about the notion of countable sets. So before we saw some sets that were finite, but there are also some sets that are infinite, like for example the naturals or the integers. And a very interesting property of infinite sets is that you can have a proper subset with the same cardinality as the bigger set. So what does it mean to say that the elements of a set can be counted using natural numbers? Well, the elements of a finite set are easy. They can be counted by defining a bijection between the set and a set that contains the elements 1, 2, 3, 4, 5 up to k for some natural number k. Now we're going to be able to count the elements of an infinite set if we can define a bijection between that set and the set of natural numbers. And this will bring us to some definitions. First, the cardinality of the natural numbers is denoted by this letter aleph, which is a letter in the Hebrew alphabet. So we read it aleph not. A set A is countably infinite if there exists a bijection between A and the natural numbers. And in this case, we're going to write that the cardinality of A is aleph not. And a set that is countable infinite is sometimes called a denumerable set. And we're going to say that a set A is called countable if it's either finite or denumerable or countably infinite. And finally, a set that is not countable is uncountable. So with this in mind, we're going to look at one of the examples that we have of countable sets. We already saw that the naturals and the integers are countable sets. Now we're going to see that a set that is even bigger than those is also countable. The set of all positive rational numbers is countable, is countably infinite. And to show this, we will need to construct a function that is bijective from the set of naturals to the set of positive rational numbers. And this is how we go about it. We're going to first create this infinite matrix. And what we have here is we have all the positive rational numbers. How do we construct them? Well, a rational number, if you remember, is just a fraction that has an integer in the numerator, an integer in the denominator, just making sure that the denominator is never 0. So if we do that, what we're having here is that if we have an entry in the ith row and jth column, then in that place we have the fraction I over j. And this is going to help us build an argument to construct our bijective function from the naturals into the positive rational numbers. How do we do that? Well, we're going to start first with the fractions I over j such that I plus j is equal to 2. In this case, we have only 1 over 1. So f of 1 is just 1. Now we're going to go and look at the fractions I over j such that I plus j is equal to 3. We have two such numbers. We have 2 over 1 and 1 over 2. So what we do is, well, f of 2 is going to be 2 over 1 and f of 3 is going to be 1 over 2. And I'm going to continue going through these diagonals, the ones that keep the sum of the row and the column constant, and I will use those to create my images. So here you see we have now the fractions I over j such that I plus j is equal to 4. For those we have 3 over 1, 2 over 2 and 1 over 3. But notice that 2 over 2 is equal to 1. It has already been included. So if I want my function to be injective, I cannot define that again. So what we're going to do is whenever a fraction is not in the lowest possible terms, we're going to just ignore it. So in this case, as you can see, I grayed out the 2 over 2, we're going to skip it. So now f of 4 is 3 over 1, f of 5 is 1 over 3. And we're going to continue going through these diagonals. So later we're going to do the ones that sum up equals to 5. So we have 4 over 1, 3 over 2, 2 over 3, 1 over 4. Then the ones that sum equals to 6, so I have 5 over 1. 4 over 2 is 1/2, so we as 4 over 2 is 2, sorry, so we're going to ignore it. Then 3 over 3 is 1, again we ignore it. Then we have 4 over 2, we have to ignore it again because it's 1/2. And then we have 1 over 5. So that is how we're going to do this. Now, we just showed, well, we didn't properly show, but I gave you an idea of why the set of all positive rational numbers is countable. Now we can extend this to the set of all rational numbers. I know that there are, in a way, twice as many, but we can show that this set is also countable if we use the fact that, first of all, the positive rational numbers are countable, and then we use an argument very similar to the one we used to show that the cardinality of the natural numbers and the cardinality of the integers is the same.